So whenever we were doing limits, we started out graphing limits and then we said we don't really want to graph anymore. What we want to do is do it algebraically. Same with continuity. We don't necessarily want to have to graph all of our functions and then decide if they're continuous, so we have laws of continuity. These laws of continuity come straight from the limit laws. So for every one of your limit laws, we're going to have a law of continuity because continuity is defined as a limit. So what we're going to do is we're going to assume that f of x and g of x are continuous at a point x equals c. So assume that two functions are continuous at c, then the following are also continuous at c. So then the following are continuous at x equals c. First off, I could just add or subtract them. So if I know two functions are continuous at a number c, then I could add those two functions together and that's also going to be continuous. So for example, we know that the function x is continuous at x equals 5. I also know that the function x squared is continuous at x equals 5. If you don't believe me, graph those, look at your limits. Those are definitely going to be continuous. Therefore, x squared plus x is continuous at x equals 5. So if you know that two functions are continuous at the same value, I could add or subtract them, also going to be continuous. Second limit law is going to be k times f of x for any k. So if I know that, that a function is continuous at a point, I know that any multiple of that function is also continuous. So for example, let's look at the function x squared again. It's continuous at 5. Which implies that, how about 10x squared is continuous at 5 at x equals 5. So anytime I have a function that's continuous at a point, any other function that's a constant multiple of it is also continuous at that same point. Okay. Third limit law is that f of x times g of x is continuous. So if I have two functions that are continuous at a point, I can multiply them together and get another function that's continuous. So for example, let's take f of x as x squared, and let's take g of x to be x minus 2. Both are continuous at x equals, let's say, 4. We can graph those and see those are both continuous at x equals 4. Therefore, x squared times x minus 2 is continuous at x equals 4. So if I know two functions are continuous at a point, I can multiply them together and get another continuous function. And then the last one, f of x divided by g of x, provided that g of x is not 0, is also going to be continuous. So with this same example that we were doing before, I know that x squared over x minus 2 is continuous at x equals 4. So those are our limit laws that we have. If you know that two functions are continuous, I can kind of put them together to build more continuous functions. Now some basic functions that we should know. Any polynomial is continuous, always. So any polynomial that I have, it's continuous everywhere. So it doesn't matter what x value you choose, it's always going to be continuous. What else? Any exponential, b to the x is continuous for b greater than 0. Now I can't plug in a negative base and have it being continuous, but any exponential is continuous for any x. Also, any logarithm. This is also continuous for b greater than 0. Alright, so we've talked about a bunch of functions that are continuous everywhere. We haven't really talked about an easy way to tell if it's continuous, and this is where a limit comes in. So here's what we'll say, and this is kind of a big deal. If you know that f of x is continuous, so if you know that f of x is continuous, then you know the limit. Then the limit as x approaches c of f of x equals f of c. And this is kind of a big deal about continuity, because when we were doing limits before, we had to use all of those different limit laws. But now we know if a function's continuous, you can just plug in that value. So, I know you've been wanting to do this the whole time. Let's look at the limit as x approaches 1 of 3x squared plus 5x minus 2 over x squared plus 1. Now, before when we were doing limit laws, you would have to say, oh, well, the limit as x approaches 1 of x is defined, so I can use the constant multiple, the power rules, and all that. But I know that this function is continuous at 1. This function is continuous at x equals 1. Since I know that, I can just plug in 1. And this is what I get. So let's see, what is this? 3 plus 5 minus 2 over 2. So that's 8 minus 2 is 6 over 2, so 3. So this is really helpful to us. The reason we spend so much time talking about continuity is because if a function is continuous, finding the limit is really easy. You just plug in that number. But again, this only works if it's continuous. So something like, let's say as x approaches 1 of 1 over x minus 1. That's not continuous at x equals 1, so I can't just plug it in. So this is not continuous at x equals 1, so you can't just plug in. You would like to, but you can't, and we'll develop other ways to do this, but for now, if you know the function's continuous, you can just plug in your x value, which is a huge help for us, because now we don't have to look at the graph, we don't have to use any of the limit laws, we can just plug it in. So that's kind of the culmination of section 2.4.